Hi, this is the first video for Class 7. In Class 7 we will see how enzymes catalyze reactions. In this particular video I will discuss the thermodynamics of enzyme catalysis, and we'll look at the reaction coordinate of the enzyme plus substrate going to enzyme plus product. In other videos for Class 7 I'll discuss the proximity model, general acid and base catalysis, and we'll also look at the mechanism of two particular enzymes, HIV protease and carboxypeptidase A. This enzyme is chymotrypsin, and why don't we jot down some notes on what we remember about chymotrypsin. We should remember that chymotrypsin is a protease that cleaves at the C side of the aromatic amino acids phenylalanine, tyrosine, and tryptophan. But there's a disclaimer: if proline is at the cleavage site, if proline is at the C side of each one of these three, then chymotrypsin will not work. Now let me jot down a couple of other notes concerning its catalysis. Chymotrypsin cleaves 190 amide bonds per second, super fast, and that is 1.7 times 10 to 11 times faster than the uncatalyzed cleavage at these amino acid residues. The last thing I want to say about chymotrypsin is that in the active site we have three amino acids that are very important for the catalysis. It happens to be histidine, serine, and aspartic acid. In other videos in Class 7, we'll take a look at the active site of other enzymes and see how, or see what amino acids are involved in those active sites. Now, if you think about the thermodynamics, right, this is more the kinetics, and that will be in Class 8. But if you think about the thermodynamics of peptide cleavage, we could say a couple things. If you recall the delta G, so it is thermodynamically favorable. Products are favored. Actually, the half-life for this peptide cleavage right here is about 20 years. Just a reminder, this means standard state. The 0. This was something new for me. This apostrophe or this prime. That means that the solution's at pH 7. Okay. So there's some interesting thermodynamics happening. It's favorable, but it's a very slow reaction. Enzymes can obviously speed this up, and we're going to see in general how they do that. Let me give you 3 ways to increase the rate of a chemical reaction. The 3 ways to increase rate of a chemical reaction is to increase the temperature, to make the molecules move faster with higher energy. Those reactants can collide with stronger force. Number 2, increase the concentration of reactants to up the probability of the 2 reactants hitting and in the right orientation and with the right amount of energy. And number 3, add a catalyst. And we're going to look at enzymes, which are proteins that catalyze reactions. Most enzymes are globular proteins, a combination of alpha helices, beta sheets, and random coil. And we saw that with chymotrypsin. That's a good picture of a globular protein. Enzymes are not the only biomolecules that catalyze reactions. Some RNA do, and those are called ribozymes. Let me show you some things about enzyme specificities. The varying specificities of enzymes are largely explained by what's called the specificity pocket, a cavity, basically, that can help draw in certain residues, positioning the bond that's going to be cleaved, which is called the cis bond. So this is part of the active site, but it's a pocket that helps specify which peptide or which portion of the peptide can fit and ultimately be cleaved. Now, we saw chymotrypsin at the beginning of the video. It cleaves aromatic amino acids, or cleaves at the C side of aromatic amino acids. So here we have phenylalanine, just the carbon skeleton. But trypsin, what do they cleave? They cleave on the C side of basic amino acids, like lysine and arginine. Okay. And you know, the specificity pocket is very similar between these two, but this one, trypsin, has an aspartic acid that has a charge interaction with the positive charge of either lysine or arginine. But the other amino acids in the specificity pocket are for the most part identical. Okay, let me just put here what it cleaves at: phenylalanine, tyrosine, and tryptophan. When you think of the active site, sure, you think of the place where the reaction happens, but also you want to think of the active site as it being specific for certain amino acid residues when they're doing, in this case, a cleavage reaction. Next, we are going to draw a reaction coordinate for a reaction where we have a very simple process. We'll take substrate. Is that what I want to do? Yeah, substrate going to product. Oh, I see what I'm doing. At first we're not going to consider the enzyme, the E. And we have a rate constants in the forward direction and in the reverse direction. And we also have an equilibrium constant where products over reactants. Okay. Next I'm going to draw a reaction coordinate for the uncatalyzed reaction of the substrate turning into the product. So here we have substrate going to product, going through what's called the transition state. It's a short-lived species. And from the substrate to the transition state, there's a jump. And that is the free energy of this, we could call it activation energy, but it's going from the substrate up to the transition state. This double dagger right here, that means that it is the energy difference of the substrate and the transition state. So this is typically an indication that you're dealing with a transition state. Another way you could represent that actually is in brackets, double dagger, like that. Now the overall delta G, right, the overall free energy is negative. Okay, so this is showing that this is favorable, right, or spontaneous. It still could be very, very long. It could take kinetically a very long time, but it is spontaneous. With enough time, eventually it will go mostly to product, or it favors product. So what does a catalyst do? Or how does the curve differ when you have something that's catalyzed? Well, you're going to lower this delta G naught double dagger, and you'll have something like this. You start out at the same level as the substrate, and you're making the same product, so you're going to end up on the same level as the product down here. But now we have a new delta G double dagger. Okay, so we lowered, you can think of it as activation energy, or we lowered the the delta G. So I do have a question concerning this reaction coordinate, and that is, and let me jot down a couple of choices. Okay, those are your choices. 1, 2, 3, 4, 5, 6 choices. And what happens when this reaction is catalyzed by an enzyme? Well, go ahead and select your choices first before I explain what I would do. Okay. The equilibrium doesn't change. Okay, the ratio of products to substrate is going to be constant if you hold the temperature constant. So these would not change. So we could get rid of those two. Now the delta G double dagger does decrease, right? The height decreases. So this is correct. Okay, we lower the activation energy, or we did I circle that by mistake? Yeah, not that. We lower the delta G double dagger. Yikes. Okay. Decrease it. Now what about the rate? So you know that enzymes and catalysts speed up a reaction. Well, that will tell me that K1 is increased. K1's increased. But eventually we're going to hit equilibrium, and K1 is still increased. Well, to reach equilibrium, K2 has to be the same magnitude, but in the opposite sign. So K2 is identical to K1 when you reach equilibrium. So if K1 is increasing, the speed of the forward reaction is increasing, the speed of the backwards reaction also has to increase. Now, do you see how that's possible by looking at the reaction coordinate? See, the jump going from substrate over the hill was lowered by the catalyst, but same thing in the other direction. The jump from the the product over the hill is also lower when it's catalyzed. So this purple, obviously, this is when it's catalyzed. So both hills in the forward direction and in the reverse direction are actually lowered, thus increasing the rate of the forward reaction and the reverse reaction. Maybe that's not as obvious without the graph. So there are only 3 answers. That one, and that one. Okay, but I drew the reaction where it's not catalyzed. What does it look like when we add the enzyme? Okay, what does the reaction look like? Let's call this section Model for Substrate Binding and Catalysis. So here we introduce the enzyme, and it's going to bind the substrate. We'll give that a K1. And then it's reversible. The substrate can actually get unbound, and we'll call that actually K-1, the reverse direction. This happens in the active site, and we have the enzyme substrate complex. Now, the reaction occurs, and that will be step 2. The substrate is turned into the product, and then it has to be released. That's typically called turnover. And that is K3. And this is K-3. Those terms, turnover, the rate of the forward direction, the rate of the reverse direction, that's kinetics. And we do have a class 8 dedicated to all kinetics. But here, we're worried more about the free energy, the delta G. So let me again draw out our reaction without the enzyme, and then we're going to show it be catalyzed, but now not only catalyzed in one step, but see, it's catalyzed in several steps. So we're going to have several hills for that catalysis diagram. Okay, I'll do this in red, It's very interesting. So we have the enzyme subs and the substrate, and they bind. We get a little bit of a, a little bit of a rise, but actually your enzyme substrate complex is pretty stable. It's lower in energy. And we have this. That's interesting. Entropically, right, we're combining two things into one thing, so it's not favorable entropic-wise, but because of enthalpy and the interaction between the enzyme and the substrate, it's actually lower in delta G. And what we could call this the delta G of binding. And it's negative. The delta G of binding. This one right here. Okay. Now we do decrease the activation energy. So we still have a hill. Okay. And again, we could think of this as a transition state. So this is interesting. The transition state for the uncatalyzed reaction is actually similar or even identical to the transition state when we have it catalyzed. That's going to be super important, probably in the next video. And we get another valley, right? If we take a look at this reaction here, we have 1, 2, 3 hills. I hope we have 3 hills. We have 1 here, 2 here, and then we have a 3rd hill. And we have something like this. And we end up, again, in the same final position with the enzyme and the product. So this is the EP complex before the product is released. Okay. Now, when we think about maybe the activation energy, what we're really interested is not from ES to the transition state, but what we're really interested in is the enzyme substrate complex to this transition state. We have this rise here. It should be, oh boy, it should be still shorter or lower than this, and I believe it is. I hope it is. Yeah, it's definitely, oops, right there. It's definitely shorter. So what did we call this before? We called this the delta G naught double dagger. And for this one, it is a delta G naught double dagger for the catalyzed process. Now, the delta G for the overall reaction is still the same whether it's catalyzed or not, and it's this delta G right here. That is a delta G of just the reaction. Maybe what I can say here, though, is that I started to discuss the entropy of this process. So we have here E plus S going to ES, and we predict that the entropy is positive, right? Because, no, not positive, negative, because we get more ordered. So it's not entropically favorable, right? We're losing entropy. So delta S is a negative. It's just that the delta H, right, of binding is so negative, so it's a larger negative, that delta G is negative. And this one is a big negative, whereas this one is maybe a smaller negative. So the enthalpy of binding overcomes the disfavorable entropy. And that's the beauty of enzymes, that it could overcome this entropy via the enthalpy of binding, of the substrate binding the enzyme.